So tutorial number 13, it's a one that I've been wanting to do for a long time, in the sense that it talks about agents. We get to the point where we're collecting all the information that we have done in past tutorials to actually structure a flock of birds, or in this case it would be balls, right? So we're going to start from tutorial number 11, that it's on the website, and you can follow the video and do it, where we have this kind of vector class of balls bouncing around. We're going to do a little bit of changes here. We're going to go inside the class, the ball. We're going to turn off gravity, just gray it out, in order to have the following. Right? So we have these kind of balls moving on the screen, just bouncing around, all of them starting in different directions. So that's where we want to be. I'm going to save this as tutorial number 13, agents. Right? So the first concept that we need to grasp here is the idea of class interaction. How does an element of a class, in this case a ball, can talk to another ball, right? Because at this stage they're all kind of having their own behavior, but they're not kind of interacting within each other. So we're gonna do a little function here that's gonna be called line between, right? And this will prove a concept for us, and then we will use this idea to actually write a much more complex behavior. But let's start with that. So I'm going to write void line between. What I want this function to do is basically just draw a line between two balls, right? So we need to think of what is the structure that, how do we actually get the information of another ball? We have a structure here that it's the array list. This is where we're storing all the balls, and this is a global variable, so we can access it from any point in the screen. So that's very convenient. So we know that I'm going to copy this name, ball collection, that is the array list, where we store that, and I'm going to put it here. What is this? This is the collection that we want to go through, right? So how do we go through that collection to retrieve some information, in this case the location of a ball? We have to do a for loop, right? So we're going to say for integer I equals 0, I smaller than ball collection dot size. This means that I'm going to go till the number of elements that it's inside that collection. If that collection has 5 elements, the for loop would be up to 5. If it's 100, we'll go up to 100, right? We've seen that before. I++. So we're going to go through every element. And I'm going to give some space to put some stuff inside this for loop. What I want to do inside this for loop is calculate a distance between the location of the ball and the location of any other ball, right? So first of all, I need to define the instance of that other ball. So we're going to say ball other, right? Equals, this refers from the class ball inside ball collection dot get I. What I'm saying in this line, and I think I've explained it before, we are kind of casting an instance of the class ball, and we're calling this other, and we're saying that element I, get me from that collection that element I. So it will get me each element one at a time through the for loop. So we can use other and understand that other is just one element from that collection. And we're going to also do float distance equals location. We have a vector that is the location, right? So through vector math, we can calculate the distance to another ball. In this case, we use the distance to. This is the way that ToxicLibs actually calculates distance. Remember that we're using the ToxicLib vector class. Other dot log. So here, other, that refers to this other, this is the instance of the class. As the class has a field called location, or loc, we can put this dot and access any of the global variables of that class. We can even access functions, right? So what I'm trying to calculate is the distance from the ball that I'm in, like this element, to all the other elements. And I'm going to do a simple if statement saying if the distance is bigger than 0, right? And I don't know if we've seen this already, but operations, I believe we have in some of the early tutorials. So we're adding some extra information to that if statement and saying if the distance is smaller, distance is smaller than 40, do something, right? What do we want to do? In this case, is a line. So we're going to say line from loc.x, from loc.y. This is the location from the position in x and in y to other.loc.x, other.loc.y. Right? Fairly simple. Where a line needs 2 points, an x and a y, and an x and a y. From the start position to the end position, we're using our position, the position of that class as the starting position, and the position of the other class, only if the distance between me and that other ball is smaller than 40 units. I'm going to add a little bit of a stroke color here, red in this case. And I'm going to also, in display here, say that the ellipse has a stroke of 0. Just for the purpose of clarity. It's just in the function display I added stroke 0, and in this line we're doing a red line. So let's see if this is working. Right. So this is what we have. At this stage what we have is just if we reach 40 units of distance, a line, a red line appears. If that doesn't meet the distance that we're asking for, the line doesn't work. We can change this value of 40 to anything, like 80, but taking into consideration that we will be adding many more lines to the system, right? So this is a first way to check that this kind of class interaction between one ball and any other, we have that communication going, right? So that's pretty good. I'm gonna, just for the purpose of some graphics here, I'm gonna say stroke weight 0.4, a little bit more subtle. I think that's all right. I'm gonna press Command T or Control T here in the PC, right, to auto format. So the only thing that this will do for you is just, as I said before, it will clean a little bit the script for you. So this is good. We have line between as a function that we have developed. And using this principle, what I want to write now here, remember that we have this function called run that is kind of a summary or even an index of the behaviors that we're adding, right? I want to add a function called flock, right? And flock, it's quite a complex behavior. It has different elements on it. So we'll go through them and we'll see how to structure them. This is based on the Craig-Reynolds steering behaviors algorithm. So you can find that in examples in processing. It's already written, but I just want to go through what does it mean, each element, how can we tune it, and how can we start using it, right? So we're going to say void flock. I'm going to write it slightly different from what you will probably find in the examples, but this is just for the purpose of clarity of how these different functions work together. So this function flock, it's constituted by 3 elements. One of them is separate. The next one is cohesion. And the next one is align. So it's cohesion, alignment, and separation. Again, Command T. These are functions. Each one of these elements are functions that we haven't written yet. This is not part of the processing commands. So we need to write each one of these functions to make our flocking algorithm work. So we're going to start one by one. Okay, I'm going to just gray out, comment out cohesion and alignment to start with separate and not get an error saying that function doesn't exist yet. Okay, so I'm going to just give some space for us to work here. So let's write the first one, void separate. Right. So the basic principle of separate, alignment, and cohesion, it's based on vector math. We've seen that in the past tutorial, tutorial number 11, I believe. 11 and 12 have been about this vector math. And what we wrote here already is kind of the perfect structure for something like separate to work. So what do we want to make them separate? We want to say if 2 balls are too close to each other under certain distance, they kind of move away from each other, so they separate, right? So we achieve that through vector math. But if you can see here, this kind of line between structure gives us everything to actually achieve that. The only thing that we need to change is this part where we draw a line. So instead of drawing a line, we will say if you reach, let's say, 40 units, you go away, right? So let's copy that. Let's copy that same structure. I'm going to copy these lines here till the if statement, right? So we have a for loop, and when you do something like this, you'll start doing stuff like this all the time. You have to be very careful with the parentheses. This is where most people have the problems, right? We have an if statement here that it's closing here. We have a for loop that it's closing here, and we have the function that it's closing here. So again, I pressed Command T just to clean our syntax here, and I'm going to leave space in this if statement because this is where I want to really write the code. We're gonna need a few other things to actually make this piece of code work. We need to start give ourselves an empty vector. So vec3d steer, we're gonna call it, right? So this is the direction that we're gonna be moving towards. New vec3d, and if I do this, it will produce an empty vector. Also, I want an integer that I'll call count, that I'm going to assign 0, right? So we're going to be counting, and we're going to use that count to actually do some math operations over the vector that we're producing. So, okay, here is the part that starts getting tricky. We need to understand the vector math. So I want to move away from some other ball if this distance is smaller than, in this case, let's put something like 30. Right? So we need to here to calculate a vector of difference, basically the subtraction between sub we're doing here, and if you remember the past tutorial, that line that connects the vector, that it's that line between our ball and another ball, is the subtraction between our location and other location. We need that vector that would make us both move towards something or against something. This is the way you do it, right? You get the subtraction between those two. Then, and this is just for making this movement a little bit smoother somehow, we're going to say normalize 2, 1 divided 1.0 divided by distance. So what are we saying in this line? We're saying that vector has certain strength based on what is that distance. We want to just divide it by the distance, so we can really scale it up, and we have a different strength of that vector depending on the distance. We will see later that we can gray out this line, and we'll have a movement that is a little bit more mechanic, but this line allows it to be a kind of very smooth movement. Steer dot add self diff. Right. So what are we doing here? We are this empty vector that we generated at the beginning. We're saying add to this empty vector the difference vector. Okay, and so this is the steer is the one we will be working with. We're going to say count plus plus. So we're saying each time you go through another ball, if this happens, add it to the count, add 1 unit to the count, and add that difference vector to this steer vector. So our ball will go through all the other balls in the system, and it will calculate if this condition happens. If it happens, it will store that vector, the vector to go in the opposite direction, in this steer vector, and it will count. Why do we need to count? Because as we're storing more and more vectors from different balls, let's say in this case we have 100 balls, so we can eventually we could have like 100 different vectors added to our steer vector, and that would be a quite big vector. So we need to scale it down. We need to divide it by the number of elements, and that information is provided by the count. So how do we do that? We're going to say if count is bigger than 0, and we do this if statement just for the purpose that, if count is 0, you don't want to divide anything by 0. We're going to say steer dot scale self 1.0 divided by count, right? So we're saying if, and only if, the count is bigger than 1, so if we have at least one ball within our 30 pixel radius, and we are storing one vector of separation, divided by the number of vectors that we have. So if we have 20, it will be divided by 20. So we can just scale that down to the real size. So at this stage we have a steering vector that we need to somehow apply to our ball, and that would be perfect, right? So we need to think of how do we make this ball move so far. Our move function, that is quite primitive actually, says location dot add self speed. That's good. But when we talk about steering behaviors, the idea of it's not only location and speed that what we need, is also an acceleration. And what is the acceleration? The acceleration will be a place where we will store in every frame all the movements that are being calculated for the ball, and we'll pass them by to the velocity or the speed, right? The speed is the actual movement, is the constant movement of the ball that affects the location. So all this sounds maybe a little bit strange, but this is what we're going to do. We need to add an acceleration, right? Vector. That it will start 0. It's just an empty. So we're going to say vector 3D acceleration equals new vector 3D. If we leave it empty like that, it's a 0, 0, 0. I'm going to navigate down again to the bottom to our move vector, and we're going to say that speed, our velocity, every frame will add to itself the vector of acceleration. Right? Also, I want to say speed will limit itself to 2. 2 representing what we could be called the maximum velocity, but just to give a threshold for that. So you can put any number here. If you want your system to really move fast, you can put higher numbers here. But it's good to have some sort of threshold so we can keep things nice and clean. So then we have location at speed, and also we need acceleration dot clear. This means that every frame we are making this sequence of events. We are storing acceleration in our functions. We're passing that acceleration to the speed. The speed gets constrained by our maximum velocity speed. We pass the speed to the location, so the location is updated of the ball, and we reset acceleration to 0. So we can reevaluate behavior. Let's say we can recalculate if we want to separate or get close to something, or any kind of behavior. So the acceleration, again, representing the calculations every frame we want to do, let's say the behavior. The speed is the actual movement that our ball is having at any point in time, and the location obviously is just the position of the ball. So the separate needs to provide its information of steer to the vector of acceleration. And how do we do that? We just, as acceleration is a global variable, right? We just need to say steer, no, sorry, acceleration dot add self steer, right? So we know that this acceleration will be passed to the speed and eventually to the location. So our function ends there. What it's really good to do as well is say steer dot scale self to some factor, something, anything, let's say 4. This line, it's allowing us to, whatever our calculation is, to really kind of increase, to have some sort of scale factor to it, you know, because as we will see, cohesion, separation, and alignment need tuning. They need to be processed through some sort of scale factor. So we're going to put this scale factor in this line here that will allow us to modify how intense this thing is. Or what we could do actually, this would be a good idea, we could say separate, and we could say something like float magnitude, right? So we will provide a float that will represent, I'm going to copy this here, right? What I'm doing is, and this is, you can go back again to the function tutorial, but if I put any information here in this bit of the function, I can use this magnitude variable anywhere in our function, but when I call the function that it's here, I need to provide that bit of information. So this is how the wire is kind of connecting this bit of information, in this case 4, to the magnitude, and eventually we're using that as a scale factor, right? So this is it's a quite neat setup because we will have separate 4 saying the scale factor is 4, maybe cohesion will have 2 or 0.1. We will see that cohesion is very small, and align maybe some. So we can tune the different strengths of our function. Let's see if this is working. We might have some errors around. Okay, it is working. So you can see that the balls, when they reach certain distance to each other, and this has got nothing to do with the lines, so please don't, let's grade out the line function, just a flock. You can see how they are kind of not bouncing, but they're kind of separating from each other. They become close, and eventually they start moving in the opposite direction. That's pretty cool. And it's very smoothed out. The movement is very kind of precise. Let's see what I mentioned before. If we kind of this line over here, where we actually normalize for the distance, what would happen if we would just get rid of that line, right? So you can see that we're still getting that effect, but it's very mechanical. We're getting to the threshold and instantly jumping in the opposite direction. This line allows us to kind of increase or decrease the intensity of that force based on the distance. So when you enter that radius, the strength of that force is very, very smooth, very slow, and eventually when you're getting closer and closer, you get to a point where it's really strong. So that's this line here, right? We could really use some curves to make a graph of what is actually happening, but for that there's some really other tutorials that could help us understand that. So let's keep moving, okay? At this stage, I'm going to turn on again the line between. There's something it looks quite good, I would say. And we have a separate function. So all this stuff I'm going to save. It's going to be in the website as all the other scripts. So if you're having any trouble, go to the website and you'll see the source code, and you can see what are you writing wrong. If you have any questions, any doubts, please comment as well on the website so we can just have a conversation of if there's any concept that it's not really clear. We're gonna go through cohesion in a similar way. So we're gonna give some space to work on this cohesion function. So we're going to have some space here for the cohesion to do it. So the cohesion function is basically very similar to separate. The only difference is that it's the opposite, right? We want to go towards where other balls are. We want to keep together. We want to be not so close to the other ball, but at the same time we want to be somehow kind of gathered around where balls are. So how do we do that? We're going to copy this vector here of steer, the first part of our separate function, and here I'm going to call it sum, meaning the summatory, right? Because there's a little bit of a difference in the script, in this function from separate, and I want to stress that. So again, I'm going to copy all these elements here. That is the structure to the for loop that we did in line between, right? For loop that goes through all the other balls, gets one of them that we call other. We calculate the distance to that other ball, and if the distance is smaller, it's bigger than 0, and smaller than 30, we do something. In this case, will be the cohesion functionality. Why do we say bigger than 0? Because as we go through all the balls in the collection, we also go through ourselves. I mean, the ball goes through itself and in that case the distance between log and log, that is our distance, is 0. So we want to rule that out of the system. So here we need to say what happens. So sum, we're going to say here sum dot add self other location. Right? What are we saying here? We're saying this is kind of the vector that will average the position of many of the other balls around me. Only the balls that will be, in this case, let's say, in a radius of 60. So I want to calculate what is the centroid vector, or the centroid point, between all my kind of neighbor balls. I will go through all of them, and I will kind of find which ones do I want to be close to. And again, we're going to use the count plus plus. Right. Remember that this count is a variable that it's inside the function, so it's got nothing to do with the count on the separate, right? So we can use the same name of variables as long as they are kind of inside this visibility. If we define them within this visibility, then the curly brackets, we can use these variables inside here, and they don't relate at all to the count that is in this other function, right? So at this stage we're kind of adding to that sum vector the position of other balls when they are within 60 units. That's good. We need to get out of the for loop, and this is very important. That many people always ask me, it's like, hey, this is not working. It's because you're doing it sometimes inside the for loop. You know, you're repeating that operation many times. So what are we going to do now? That is divide that summatory vector by the number of elements that we counted. Needs to happen outside the for loop. So if count is bigger than 0, sum dot scale self 1.0 divided by count. Right? So we're again the same thing that we did before. In this case, just to get the average position of where the balls around me are. You know, so we want to just steer towards one and only position. That is the new sum vector. For that, we're going to say vector 3D steer. In this case, this is again the vector that we want to use to move our ball. We're going to say location dot sum dot sub block. Right. We're doing a subtraction, and again, if you go through the vector tutorials, it's the same operation that we're doing in separate. It's the line between our position and our target. This is the subtraction between these two vectors. I'm putting them in this order. That is the opposite order that I use in separate, because I want to go towards sum. Before I was just running away from the location of another ball, right? And in this case, this is a kind of a, I want to move there. I want to just get to that point. So I'm inverting those two values. So I'm going to say steer dot scale self, and this will be our scale factor. I'm going to put a 1 for now, so we can see a little bit of what's happening. And the same ending that we did for separate. So acceleration dot add self steer. Right. So for a second, I will turn off separate, and I will just see if cohesion. I mean, this is the beautiful part, I would say, about this kind of index structure, because you can really gray a whole function out and just concentrate and focus on one of these modules of behavior, right? So we're going to see this is working. Right, so it is. We can see that the cohesion, just by itself, makes different balls try to find each other. So in this case, there's nothing keeping them apart from each other, and they become so close that they become a point. So what if we mix this with the separate? Okay, we're still getting the same thing, but this is because it's a very, very strong force. So what if we bring down the cohesion magnitude to a smaller value? Okay, it's getting better. Cool. I'm gonna do what I did before. I'm gonna put here magnitude, and here cohesion float magnitude, and here I'm gonna put 0.001 less, and even like and 5 for separate. So now I'm seeing that these two functions that are affecting the behavior of the ball that's more like it. They want to keep together, but they don't want to really kind of bump into each other. So we're having a cohesion and separation. And this is kind of start becoming a more interesting behavior for these balls. It's still not a flock, because flock needs one more ingredient, that is our align, that will build some directionality. It will make them kind of follow each other in terms of direction. So we're gonna add that layer now. Okay, that's good. So let's right here void align. Right. And as I've done already in these other two functions, I'm gonna copy all this stuff here. Right. I'm gonna recall it steer, because in this case, so let's go from the beginning. We build an empty vector of steer. We build an empty count that starts in 0. We open up a for loop to go through all the other balls. We get each one of the other balls. We calculate the distance between ourselves and another ball, and if that distance is smaller than, in this case, 40 or something, we do something. What is that something that we do? We align. How do we write this align? What we need is to say steer. So this is our vector in the direction, right, that we're gonna aim to. We're gonna say at self, right? But in this case, we're not kind of doing an operation with the location of other steer. We are kind of trying to mimic the directionality. So we're gonna use other dot speed. Speed is the directionality that any ball at any given time is having, right? So it's like an arrow that is showing in which direction this ball is moving. So this is what we want to mimic. So we're going to do the same operation of storing this information in our empty steer vector, and also count plus plus. So we know that we have stored 1, 2, 3, 5 elements, etc. So we can do the same thing again of dividing that collection of vectors into the number of elements that we counted. So if count 0, right? We're going to say steer dot scale self to 1.0 divided by count, right? And the last bit of this function, it's passing on this to the acceleration. First of all, we're gonna use that same technique, steer dot scale self magnitude. I'm assuming that you remember that how we did it last time. Magnitude will be put here as a float, right? So this will be our scale factor for the function, and we're going to say acceleration dot add self steer, right? So when we call the function, we need to provide a magnitude. In this case, we're going to say something like 0.1, might be enough. And before I run it all together, I want to just gray out the other two to see just by itself if this element is working. So what is happening here? You see that how these balls here, they're starting to kind of average and start moving in the same direction. If I make this kind of magnitude much stronger, you will see that that will happen faster, right? And they're moving as a pack, all in the same direction. That's interesting. I'm going to leave it back in 0.1. But I'm going to turn on these other bits, these other modules of behavior. Separate, cohesion, and alignment. So we can have, in this case, something that resembles a little bit more a flock of birds. At this stage, yeah, these three things are working quite nicely together. We have the bouncing condition on the edge. You can change that to a wrapping condition that let's say they disappear and appear on the other side. Try to, as an exercise, if you don't know how to do it, try to think about how would you make them disappear on one side and appear on the other side. This would be driven only by the bouncing function. I turned off the line between just to see these balls moving, and we can see what it's this flock somehow how it's working. So that's pretty good. I'm gonna just finish. I'm gonna change the size of this ellipse to 10, and I'm gonna do a few more, like back in the main tab when I define the population. That in this case is 100. I'm gonna type 200 to see that this behavior, even if we increase the number of agents, should be consistent. This is something that is happening to all of them. So we have a flock. Again, you can see how much your computer can handle, but you can start getting some really beautiful animations of these systems when you increase a lot the resolution, the populations. Take in consideration that as the algorithm is doing a for loop across all the other elements in our script, so we have 500 elements. Think that each one of them has to make a for loop through 500 other elements. So that's why it starts becoming a kind of a very slow algorithm when you start increasing the number of agents. And there's ways to go through that, but in general, it's important that you understand what is kind of the performance of the algorithm and the computation that you're driving. So I'm going to leave it like that. Again, maybe turn on that line between function where we can really make a distance of 14 or to go too crazy with that. I hope you liked it. Again, check the genware.com website where we'll be posting this script as well as like the latest reviews and information that we have been developing both within BioThing and DAA, the DRL. So I hope that you guys like it.